Hello everyone, my name is Pedro Pessoa. I'm talking to you from University of Albany in New York, and I would like to thank the organizers for giving me the opportunity to present this work here at this conference. Today I'm going to talk about how entropic dynamics yields reciprocal relation. I would like to start by talking about the relationship between the exponential family of distributions and the method of maximum entropy. The method of maximum entropy, arising from physics, is a method to assign and update probability distribution by maximizing this entropy functional with constraints on normalization and the expected value of a few functions. This leads to the Gibbs distributions or the exponential family. There are two different names for the same thing that we can see here in equation 2. The Q is our prior for the maximum entropy process. The lambda I are the Lagrange multipliers associated with each expected value constraint, and AI is what we know in statistics as a sufficient statistics. Z is the normalizer, or, as we know from physics, the partition function. Gibbs distributions have some interesting and useful properties. First, we can relate the expected values of the sufficient statistics and the Lagrange multipliers here on equation number 4. When we invert this equation 4, we can use the expected values as the parameters for the Gibbs distributions instead of the Lagrange multipliers. Second, if we calculate the entropy for the Gibbs distributions in terms of the expected value, which is going to be the maximum entropy that we discussed before, we get to equation 5, which is the Legendre transformation between F and entropy. This is what we're going to call the macrostate entropy, and it's the one that we know from the statistical mechanics. Now, I would like to comment on how we can identify many well-studied probability distributions as a particular case of the exponential family, as we have in this table here. Even though MaxEnt was developed as a way to understand statistical physics as a theory of information from James, it's of general applicability, and it has been used beyond physics. A few examples: it has been applied to ecology, as in the work of John Harter, to economics, as in the work of Amos Golan, and complex network, as in the work of Ginesta Bianconi, and there are far more examples. Now, these applications of MaxEnt are on static models. The question we address here is whether we can develop MaxEnt into a dynamical model. That's where entropic dynamics comes. In entropic dynamics, we find the dynamical system through the maximization of entropy. This idea has been successful in obtaining dynamical models in quantum mechanics and quantum field theory, and in particular, there is this relatively recent work on entropic dynamics for dynamical models in finance. The question we will tackle here today is whether we can create a general dynamics of probability distribution. Just as MaxEnt is not restricted to statistical physics, is entropic dynamics able to create more general dynamical models? In order to talk about the dynamics of probability distribution, it's important to talk about information geometry. Mainly, there is a differential geometry structure to probabilities. We map a family of probability distribution with a finite set of parameters. In this case, we use the capital A, which are the expected value from MaxEnt, as our parameters. This way we can describe the manifold of all probability distributions in terms of A. The metric tensor of this manifold is the Fisher-Raw information metric, here in equation number 7. And the distances found from this metric are a measure of distinguishability between probability distributions. It's important to know that this geometric structure is unique. It exists no matter you want it or not. The work of Chenkov proves that this is the only metric tensor that is in accordance with the grouping property of probability distributions. If we calculate the Fisher-Roll metric for distributions in the exponential form, we have some very useful results. First, the metric is going to be the covariance matrix between the sufficient statistics, as we have here in equation number 10. Second, and specifically to these coordinates, we can calculate the metric as the Hessian of negative entropy in respect to the expected values, and the inverse metric is the Hessian of f with respect to the Lagrange multipliers. With this in mind, we can move into the dynamical process. We are going to say that our probability distribution changes. So far, we have not discussed how do they change, nor what makes them change. With this already established statistical manifold, we'll call, as in statistical mechanics, the variables x, the original space where we did MaxEnt in, as microstates, and the probability distributions defined over it, the elements of the manifold, as macrostates, which are parameterized by the coordinates capital A. Again, every set of expected values, every set of A, gives you a probability distribution. Our dynamics has to account for both the changes in the macro state and the ones in the micro state. So the entropy we maximize, that accounts for both, will be the entropy of the transition probability from a pair x and A to another pair x prime and A prime. The dynamical process is done when we find the transition probability. Now, in order to find the transition probability through maximum entropy, we need to set a prior and a constraint. Our prior is that the system moves continuously. What I mean by this is that we are going to separate the prior into the prior for the micro state change and the macro state change as an independent motion. The prior for the micro state is just going to be the MaxEnt prior that we defined before. And the prior transition for the macro state will be assigned in this prior in equation 14, which is what defines a continuous motion. For an infinitesimal small step, we need this parameter tau going to 0. G to the 1/2 is the volume element, as G is the determinant of the metric. For the constraint, we must be so that the motion of the probability doesn't leave the statistical manifold defined. We implement this by saying that the posterior probability for x prime has to be of the exponential form with respect to the macrostate A prime, as we have here in equation 15. Now, it must be said that here we only have the simplest possible constraint. If we are modeling a more complicated system and you need to account for something known, some information on the motion, we might want to change the constraint or the prior. When we maximize the entropy and find the transition probability, taking into account only the transition in the macro state, we obtain the transition found here in equation 16. Remember, here S is the macrostate entropy or the entropy of the Gibbs distribution. Now, we are going to take this parameter tau as our entropic time. Note that we are not making a dynamics on an established time. The entropic time is an object that arises from the system, and in equation 17, we see that it measures the system's fluctuations. With this time established, we can write the transition in equation 16 in this useful form of equations 18 and 19 as a differential equation where the flux or the velocity v has two terms. The first is what we're going to call the entropic drift that leads distributions to the maximum of macrostate entropy, while what we call the osmotic term is derived by differences of density of probabilities. This is a diffusion equation in the statistical manifold. Here is where we should talk about reciprocity, as in the title of the talk. The change in the expected values for our dynamics yields this interesting relationship here in equation 20. The entropic time change of our macrostate parameters is proportional to the gradient of entropy in the first term, and the proportionality term are the terms of the information metric. This compares directly to what is known in non-equilibrium statistical mechanics as the Onsager reciprocity principle, where the time change in a macrostate parameter is near the equilibrium value, A star, proportional to the gradient of entropy with a symmetric proportionality matrix. Now, Onsager reciprocity is usually derived from supposing a time reversal symmetry in the macro state dynamics, which makes sense in a physical system with a Hamiltonian. But in entropic dynamics, reciprocity arises directly from information geometry. The proportionality constant is the information metric, and the second term is also geometric, the Christoffel symbol that accounts for the curvature of motion. Here, this first term reciprocity is a consequence of maximum entropy, is a consequence of information theory, and not supposed as a principle. This implies that the reciprocity here can, in principle, be extended to a far broader range of dynamical systems. We can also comment on how entropic dynamics leads to a diffusion process that, in linear near the maximum, reduces to Onsager relations. This is a parallel of another idea in non-equilibrium statistical mechanics called the Onsager mashup process, that also supposes a diffusion in the space of macro states where the expected linear terms are given by reciprocal relations. The main difference between the two is that in entropic dynamics, diffusion is a result of maximal entropy of the transition probabilities, while in Onsager mashup is only expected as a mathematical extension of Onsager away from equilibrium. Now, in conclusion, we see that we identified the entropic dynamics reciprocity as a consequence of maximal entropy, as entropic dynamics derives from information theory a dynamical process. This reciprocity, meaning the fact that the proportionality terms are symmetric, is because in entropic dynamics they are just the information metric. So, reciprocity is a direct consequence of the information geometric structure. Now, just like reciprocity has an important range in physics, it's remarkable that it can also be found to more generic dynamical systems through geometry. Now, I would like to comment on other papers on entropic dynamics. First, these results about reciprocity are found in this first paper, appearing in the proceedings to this conference. If you want to see talking about how this entropic dynamics of the exponential family was defined, you can take a look at this first paper here. On this second paper, I have an application of this entropic dynamics framework to the problem of complex networks. And in this third paper here, I make some important calculations necessary to apply this entropic dynamics in ecology. Thank you very much. I would like to give special thanks to all of these colleagues who helped me through the development of this work. And thank you for watching.
Thank you.
All right. All right, thank you. We have the speaker Pedro Pessoa connected online. So please let me know if there are questions.
Up. So there is any question here? We have one question. Can you come here? Because we cannot hear on Zoom. And just put the mask.
And look at the camera.
Or just speak for this one.
Okay.
It's okay.
Hello, thank you for the nice talk. So I don't know much about it, but should I think about this entropic dynamics as a first order dynamics or like second order dynamics? Like it's like a dynamics of a gradient in the entropy, gradient flow basically, or there is an actual acceleration and then an effect of possible.
Neither. When you think about first order and second order dynamics, you're thinking about velocity and acceleration, just like you said. But as I do entropic dynamics, this is a general dynamical system for probability distributions.
Yeah.
So
okay.
in principle, I don't necessarily need to have a first, second, or n order. It can be done.
I think you're still doing this first order, right? Dynamics. So I mean,
yes.
Okay.
The result that we get is that when I do the first order, I get the same thing as Onsager reciprocal relations.
Okay.
And when I assume that my movement is continuous, it follows that you have a second order or a diffusion. And in that second order, I get the Onsager mashup or something parallel to Onsager mashup.
Okay. So another slide comment on it. Do you think you can generalize this approach by adding extra costs, which are not just the entropy, which is more like a potential, something like kinetic as an energy, or with kinetic, some other purely information theoretic object?
Yes, the kinetic ends up following as a consequence of the fact that my trajectory is continuous.
Okay. Well, I have to.
Yeah, but if you want to use this to model some other kind of, like you said, like potentials, yes, you're going to have to add new constraints or costs in the maximization process.
Okay, thank you.